Welcome to In 5 Minutes. The second FM demodulator is called double slope detector, or it is also famously called balanced slope detector, simply because it will balance out the non-linearities that were present in the previous circuit, and hence the conversion from FM to AM will be more linear in this particular case. The circuit of balanced slope detector is as shown on the screen. As you can make out, that there are two different bandpass filters used on the secondary side, and both the bandpass filters are tuned to the different frequencies. So we'll discuss what are those frequencies. As of now, let's try to understand the entire circuit first. You can see for every bandpass filter that we have on the secondary side, we have got an envelope detector circuit present. So you can see the first envelope detector is formed of D1 and the corresponding components, let me call them R1 and C1. The second envelope detector is made up of components D2, R2 and C2. So in short, both the parts of the upper and the lower part of this entire detector will be acting independently as single slope detector. So what we will first obtain is some voltage across C1, let me call it VO2, and some voltage across C2, let me call it VO1 and VO2. So you can see, because diode D1 is placed in the upper branch, VO1 will have the polarities plus towards the diode branch and minus at the bottom. VO2 will have the polarities which will be opposite to VO1 because diode D2 is placed in the lower branch. So there will be positive polarity in the diode branch and negative polarity at the other end. So once we get the FM to AM conversion, which will be taking place across both the halves of the secondary, because we are using bandpass filters in both the halves. So both the halves will give you FM to AM conversion. So basically AM signal is present across first half as well as across the second half of the secondary coil. From the upper side, AM will be demodulated to give VO1. From the lower side, again the same AM signal will be demodulated to get VO2. Now this VO1 and VO2 will be distorted waveforms because they are coming from the single slope detector circuits, two individual single slope detector circuits, and hence there will be large distortion due to the non-linearities in VO1 and VO2. But if you look at the final output VO, it is not equal to VO1 or VO2. If you observe carefully, VO, which is my final output voltage, will be equal to, if I define the polarities plus at the top and minus at the bottom, then you can see the polarities are exactly same as VO1 polarities but opposite to VO2 polarities, and hence VO will be nothing but VO1 minus VO2. So when you do this subtraction, this is what I was talking about earlier. There are nonlinear distortions present in both VO1 and VO2, but when you subtract them, that nonlinear distortion will reduce to a great amount, and your final voltage VO, because it's a subtraction of the two voltages, will be much more linear output of the whole circuit. So VO is my final demodulated signal, which is coming from the input FM signal, and because it is obtained from two different output voltages with the help of subtraction operation, the linearity of FM to AM conversion will be much better, and the effect of non-linearity in VO will be very less. Now let us try to understand how should be the tuning of the two bandpass filters. It cannot be very much similar to the previous case. In simple words, both the bandpass filters cannot be tuned to the exactly same amount. We want VO1 and VO2. After subtraction, we want it to be my final demodulated signal, which is similar to the original modulating signal. So for this subtraction to give us a proper desired modulating signal at the output side, let's see how should be the tuning. Now we have very briefly already mentioned the tuning of the two bandpass filters. The center frequency of both the bandpass filters will be FC plus delta F, and for the second one it will be FC minus delta F.